In this section, we'll compare PPO and DPO, two important approaches used in RLHF to align large language models with human preferences. Think of this as a practical visual guide to post-training. How models go from simply predicting text to responding in ways people actually want. If you're preparing for AI roles or interviews, understanding this difference is especially valuable because alignment has become a core part of modern LLM development. The core challenge is alignment after training. A pre-trained language model is really just predicting the next token. So by itself, it doesn't truly follow instructions or reflect human values. We start with supervised fine-tuning, where the model learns from human-written examples, but that still misses subtle preferences. That's where RLHF comes in, using human comparisons to guide behavior. So the progression is pre-train, then SFT, then align with methods like PPO or DPO. Chapter 1 introduces the classic RLHF pipeline built around PPO, the approach popularized by InstructGPT. The idea is a 4-stage training loop. First, collect demonstrations, then train a supervised policy, next, learn a reward model from human preferences, and finally, optimize the policy against that reward using PPO. This became the standard recipe for aligning language models with human feedback. Here's the PPO-based RLHF pipeline at a high level. First, we do supervised fine-tuning, or SFT, on demonstration data so the model learns a strong starting behavior. Next, we collect human preference pairs and train a reward model to predict which outputs people prefer. Finally, PPO uses that reward signal to optimize the policy, while a KL penalty keeps the model close to the SFT baseline and prevents excessive drift. Here are the 4 moving parts in PPO. First is the policy model, the language model we're actively training to generate responses. Next is the reference model, a frozen supervised checkpoint that helps measure KL divergence so the policy doesn't drift too far. Then we have the reward model, trained on human preferences to score each response. Finally, the PPO optimizer updates the policy to improve reward while staying within that KL constraint. The KL penalty matters because it keeps the policy from drifting too far during optimization. Without it, the model can exploit the reward signal and produce strange, high-scoring outputs, a problem known as reward hacking. With a KL penalty, the policy stays closer to the reference SFT model, which helps preserve fluency and coherence. In practice, it penalizes large per-token deviations and balances reward maximization with overall stability. Chapter 2 introduces direct preference optimization, or DPO, as a much simpler alternative to the full RLHF pipeline. Instead of training a separate reward model and then running reinforcement learning, DPO learns directly from preference pairs with a single objective that looks more like classification. The result is a cleaner, more efficient way to align models with human preferences, while avoiding much of the complexity of the traditional approach. DPO simplifies the alignment pipeline. We begin with a supervised, fine-tuned baseline, then collect preference pairs, a chosen response and a rejected one. Instead of training a separate reward model and running an RL loop, DPO directly optimizes the policy from those pairwise comparisons. Using a closed-form reparameterization, the reward is implicit in the policy itself, which makes training simpler, more stable, and easier to maintain. Here's PPO and DPO side by side. PPO uses an explicit reward model, a policy grading objective with KL control, and it generates new samples during training. That makes it powerful, but also more complex and sometimes less stable. DPO is simpler. The reward signal is implicit in the loss. Training looks like classification on preference pairs, and it works offline. So, in practice, DPO is usually lighter to run and easier to tune. Here's the clean contrast to keep in mind. With PPO, you first learn a reward model from preference data, then use reinforcement learning to optimize against that reward, while KLL regularization helps keep the model from drifting too far. DPO starts from the same preference data, but skips the reward model and the RL loop entirely. Instead, it directly learns to prefer chosen responses over rejected ones. In Chapter 3, we shift the focus to why hiring managers care so much about what they see in a candidate. At the end of the day, they're not just filling a role. They're trying to solve problems, reduce risk, and build a strong team. Understanding their perspective helps you present your experience in a way that feels relevant, credible, and valuable from the very start. In an interview, knowing PPO signals that you understand the classic RLHF pipeline, reward modeling, KL regularization, and stable policy optimization, basically the full InstructGPT-style setup. Knowing DPO shows you're up to date with newer preference optimization methods that are simpler, cheaper, and widely used in open source tools like Hugging Face TRL. And if you can compare both, that shows real systems thinking around alignment trade-offs, engineering cost, and evaluation. Here are 5 differences to know cold. First, PPO needs an explicit reward model, while DPO bakes that preference signal into the objective. Second, PPO is more complex, with several moving parts, versus DPO's simpler training loop. Third, PPO uses a reference model to enforce KL control. In DPO, that role is lighter. Fourth, PPO is reinforcement learning, while DPO looks more like classification. And finally, DPO is usually easier to reproduce with open source tools at smaller scale. Welcome to Chapter 4, where we'll focus on what to build for your portfolio. Up to this point, we've covered strategy and presentation. Now it's time to talk about the actual projects you should include. We'll look at the kinds of work that best demonstrate your skills, show your thinking, and make your portfolio feel relevant, credible, and compelling to the people you want to reach. Here's a practical portfolio path for alignment work. Start with an SFT baseline by fine-tuning a small instruction model on demonstration data. Then build preference data by collecting chosen versus rejected response pairs. Use that to run DPO and compare behavior before and after training. If you want to go further, add PPO by training a reward model and measuring the extra complexity against quality gains. The real value is documenting what changed, what broke, and why. When you describe your project, focus less on the tool you used and more on the question you answered. Instead of saying, "I trained a model with DPO," frame it as a comparison of post-training methods for preference alignment and highlight the trade-offs you measured, like implementation complexity, training stability, and response quality. Then ground that framing with clear evaluation metrics: pairwise win rate, refusal quality, helpfulness scores, and style consistency or output drift. Welcome to Chapter 5, where we'll look at some of the most common interview questions you're likely to hear. In this section, we'll break down what employers are really asking, why these questions matter, and how to answer them clearly and confidently. The goal is to help you feel more prepared, more polished, and ready to make a strong impression in any interview setting. Here are a few key questions to be ready for. PPO needs a KL penalty, because without it, the policy can exploit the reward model and produce high-scoring but incoherent text. Even with DPO, a reward model can still help with filtering, rejection sampling, and reward control. You'd usually choose DPO for simplicity, stability, and lower compute, and common failure modes include verbosity, over-refusal, repetition, and trainer bias artifacts. Here are a few resume bullets that highlight the alignment work clearly. I built a preference data pipeline using chosen and rejected response pairs, then trained and evaluated DPO fine-tuning with Hugging Face TRL. I also studied KL-controlled PPO in the style of InstructGPT, compared post-training approaches with pairwise preference evaluation, and documented the practical trade-offs, especially around stability, compute cost, and output drift. Here's the bottom line. PPO is the classic RLHF approach. It learns a reward model, then uses reinforcement learning to optimize behavior while keeping the policy from drifting too far. It's powerful, but also more complex to train. DPO is a simpler alternative that learns directly from preference pairs, without a separate reward model, and is often more stable. The key takeaway is to understand both, implement one, and compare them in practice.